I'm going to be presenting to you a few different examples of how we can use Nexus Copy Number in sort of a case review format. Before we begin, I just want to give a very brief overview. This is a typical workflow that you would use for copy number analysis with Nexus. First, you would take your raw data for pre-processing. Array platform. This includes Affymetrix, Agilent, Illumina, and also we can get copy number information from your exome or genome sequencing data. From here, this raw data is interpreted. We get the log ratio value and then the segmentation to determine the copy number changes. At this point, we can also integrate the co-visualization of any sequence variation you may have from exome sequencing, genome sequencing, or targeted sequencing. At this point, we're going to identify regions of change, genes within those regions, and possibly some functional information. At the level of the regions or genes that are altered, we can also query these aberrations for anything of interest. We can do internal queries with Nexus DB, and some of these projects that we have to query involve ISCA and ICCG database projects, as well as TCGA and GeoData sets. We can also link out to external search engines, and this includes Ncbi, Google, and Ensemble. Oh, here we go. Okay, so I'd like to now take you through a live demo of Nexus with our first sample review. Sample number 1 is a female that was diagnosed with the autism spectrum disorder and mental retardation. The proband mother and father were tested using Affymetrix SNP 6.0 array. Because both of the parents were unaffected and other family history, here I'm showing you our main dataset tab. I've preloaded these samples in for us to save a little bit of time. When you're starting fresh with a new sample, we can use the data loading guide. To do that, all we do is click Load, Data, select the array type that we have. For this example, it would be Affymetrix cell. For all of these samples that I processed today, I use the default loading guide settings. So I clicked let this stay clicked here. It was a non-mosaic sample since this is just normal, not tumor. I left this at average. Perform systematic correction is checked, and so I selected my array type. Systematic correction helps to remove any waviness that might be occurring in the background due to the inherent qualities of the array. This has to do with the local GC content around the probe. We've covered this topic quite a few times, both in our blog and in other webinars. So if you're interested in learning more about it, I'd ask you to please visit our website. In any event, I always recommend that you always run systematic correction. It really can't hurt anything. It can only help. So I've selected the array here. If for whatever reason when you're using this you don't see your array, or you have a custom array, just send an email to support@biodiscovery.com and we can create this file for you. Okay, so once I've set up my loading guide up here, I view our first family trio. Okay, so right now we can see we have the sample IDs, we have the status of the samples saying that they're all processed, and our data type. Okay, and so here we can see our results. Let's just click the slider bar over so we can zoom in a little bit. So right now we can see that we have these identifiers here, which are just the sample IDs. This is useful if you know which sample is which, but for our purposes right now may be a little bit less useful. We can also see over here that we do have some loss on this X chromosome in the father. This is expected because he's male. However, I am interested to know if there's any changes in here that might be leading over to the proband. So I'd like to also perform a sex correction. So what we can do is go back to the Dataset tab and add some factors to help us clean up the data a little bit. So to do this, all we do is click on Factor, Add a Factor, and we're going to manually add in several factors. So the first I want to add is study. I want to make sure we can keep track of which study these all belong to. So we're going to call this one ASD for Autism Spectrum Disorder. So in your clinical setting, you may want to add identifiers here indicating baby date, time stamp, information that you wanted to add in. I'm going to add one for gender, so we can correct for the male. And I'm also going to add in a new name. I'm going to call it sample ID, and this is what I'm going to actually have as my display name so that I can know exactly which sample I'm looking at. And this is really useful for just keeping track of everything. I'm also going to right-click here and select Use as Display Name. So now when we look at these samples, we're going to be able to see this display. I've changed the gender. You can see it's now unprocessed. It'll reprocess and adjust that X chromosome so that it will not show the loss. And we'll be able to review all of these samples again. So right now, Nexus is reprocessing for the gender. And so we can correct for that loss of the X. This is always a really useful technique because it's going to allow you to see the changes that are occurring independent of the normal gain and loss that we would observe in differences in gender. Okay, so now you can see everything was processed very quickly, and we now have our proband, father, and mother. Okay, and so now let's have a look at the data. We also have allele calling on the bottom, yellow for loss of heterozygosity, purple for allele. In most labs, what you would now do is go and cross off to see which person it was inherited from, or if it was a de novo CNV. This is kind of a tedious task, as I'm sure you're well aware, and it also can be a bit error-prone because you have to make sure that you have everything lined up exactly correct and that you don't miss anything. So one thing that I actually like to do is to use some of the tools within Nexus to help filter out some of these calls. So the first thing that I'm going to do, because we're interested in the copy number changes only, I'm going to filter out all of these loss of heterozygosity and allelic imbalance results. So I'm going to go over here and click on this button at the funnel, to the filter option. You can see here we have a number of different filters that we can apply. We have copy number related filters, allelic related filters, and also region-based filters. So first I'm going to apply this allelic event filters, and I'm just going to remove all of the allelic event calling, since we're really going to be focusing on copy number calls for this particular case review. So after I click OK, you can see now all of the yellow and purple has disappeared. Those calls aren't gone forever. They've just been masked for this current view. Okay. And I would like to also mask all of these calls from the proband. So what I did to do this is I created a bed file of all of the calls for the father and the mother. And I'm going to now apply it to the, all of the samples so that I can remove those calls. Creating a bed file is a really simple process. What I did to do that is I clicked on this table button right here. And when I do that, it's actually making a table of all of the calls that we can see here. I took all of the calls for the father and the mother, but not the proband, just the father and mother. And the mother. Took all of these calls and created a table just of these chromosomal regions. So it's basically just modifying this TXT exported file and dropped it into the correct folder, and I can now load that as a bed file. It is, again, a really simple, easy process. But what we can do now is if I click Filter and go down here to Region-Based Filters, there's an option here, Remove Copy Number Events which are covered by region. And then it says Select Region. And now I'm going to scroll down to my custom bed track that I created, which was parental. So again, this is a track of all of the copy number changes that were found in the mother and the father. And when I apply it, what we'll see is all of the father and mother calls will go away. So as you saw, that was a really simple, easy way for us to filter out and look at just these de novo calls. Now we can look in the proband, and we see we have a couple of different calls that could be of interest. We can just click on each one of these individually to view them up close. So here we can see we have this region of gain. The probes look to be good, that they are gained, and they're not at the baseline. And we could go through these one by one, or we can actually drill down into the proband and look at these in a little bit more detail in a table view. So what I'm going to do is click on this blue hyperlink and open up the sample drill down window, maximize this window for us to see a little better. So here we have our overall sample info. We have an overview. This is the same view that we saw before, but in a chromosome chromatogram view. We can see we have the blue gains and the red losses. Our filter button is still red because we still have that applied filter we set up before. If we click on the whole genome, we can actually view the probe level raw results. So here this is just showing us all of the probes and their calls, and we can zoom in around here if we want to. But what I want to draw your attention to is this chromosome tab. Okay, so now we can look around and see what we have. We can click through each of the individual chromosomes to see the changes, or we can look at the bottom. And so here we have on the bottom all of our copy number changes that are de novo in the proband. So we have the chromosome region, the type of the change, the length of the change, cytoband location, percent CNV overlap. This is important. This is telling us and the amount of heterozygosity at that region. So even though these are all changes that are unique to the proband, we know that there are many regions in the genome that are commonly copy number variable and are most likely to be less likely to be as. So what I'm going to do is click on this button right here, and I'm going to sort by the percent CNV overlap. I'm really interested in these calls that are less likely to be that may have the potential to be more significant and are less likely to be just a common nucleotide variant. Okay, and so we have this one on the top here that has a percent CNV overlap of 18%. So this looks like it could be interesting. If we go over to the chromosome region and right-click, we can show region in Nexus, and you'll see this top panel is now going to jump to this call. Okay, so let's minimize this part a little bit so we can see in a little bit more detail. So now we've jumped to this call. It's a loss, and this gene shank. See that there's a little bit of loss of heterozygosity in this region, as we don't see any calls in the middle, which we would expect to see in a single copy loss. So the first thing that I'm actually interested now in learning more about this call is I want to know, has this loss ever been reported anywhere else? And there's a few different places that we can go to look for that. So one thing we can do is we can query Nexus DB. So let's go back to our main screen. Nexus DB right here is a database that we can use to, sorry, type in my login here. Nexus DB is a database that we can use to query other known public projects. So this, like I said, includes a number of different projects that have been deposited for public access. Okay, so while this loads, let's just click back into our window. Okay, and so what we can do is we can actually use this query button at the top here. Right here, this is going to query the database, and we'll be able to search Nexus DB to see if this loss has been found anywhere else. All right, so let's go back over here and select our projects. Once we've logged into Nexus DB, you're going to first see this page. If we click on Visible Projects, this is going to show all of the different database projects that we can query. I'm going to sort by the organism because I want to be here at the top of my screen. That's what this project is in. Okay, and then I'm going to pick any projects that will be of interest. So I'm going to start with these AGRE projects, and also these ISCA projects. Okay, and you can see I can really click and query whatever I want. I'm picking and choosing here for this example. So once I've selected the ones that I want to query, I can now go back here to my drill down view, click on this button, Query Database, click on the loss, and now what's happening is that Nexus is running a search in all of these samples to see if that loss has been found anywhere else. And so among all of those samples, those projects, we queried 48,000 samples. So it was a very, very fast search for 48,000 samples. And 2 of these samples also had a loss in this region. We can see here now the first tab has the list of the projects that it was identified in. You'll remember that we selected about 8 or 9 projects. Only 2 projects had that change, so that's what's shown here. If we click on the Samples tab, it's going to tell us a little bit more about the individual samples that had the change. If we click on All Sample Calls, it's going to show us which samples actually had that call. And what we can see here, if I just queried, and then these are the regions of loss in the other samples. You can see down here is the window size of the area that's shown, or we can also look up here at the length. So our loss was about 100 kb, and these were 2 to 7 megabases, so a bit larger than the loss that we are noticing. And if we click on this aggregate view, it will give us just a summary of those results. So it looks like there have been losses reported in constitutional cases in this region before. However, the size is a little bit different. So it looks like this might be something we still want to consider looking at, but I think I still need a little bit more information. So the next thing that we can do is we can actually click directly on this, and we can link out to an external database. If I just click on it, it's going to open Ncbi. If I right-click, I can link out to the browser of interest. I actually do want to go to Ncbi. That's my preferred browser for these types of searches. So what happens is when we go to the Ncbi search, it's now going to search for that gene term. We have on the top panel, let's run a literature search in different databases, so we can see any publications that are relating to this gene. I'd like to draw your attention to this second part, which is the health category. You can see that there are 5 records in OMIM for SHANK2, as well as 3 in ClinVar. Three results in ClinVar and see what they have to say. Okay, so we have our gene here, SHANK2, and you can see there's been a sequence variant as well as 2 small deletions that have been found in SHANK2. They all have an autism phenotype, and they've all been clinically classified as being a risk factor. So we are also looking at an autism phenotype, so it looks like this might actually be something that we'd want to report. We can also go over to our OMIM results and see if we find anything interesting here. And if we click on that top one for SHANK2, we can see that when we look here in this molecular genetics section, that it's involved in mental retardation and autism. So it looks like this is perfect. This is exactly what we want. So now we've found our significant variant, and we can go on and report it. Okay. So let's look at another patient, another case review. First, I'm going to just clear out these filters, since we're going to be looking at a new case. And let's close this window. Okay. So sample review number 2 is an 8-year-old male with Osteogenesis Imperfecta. This is also known as OI, or brittle bone disease. He has consanguineous parents related as second pathogenic sequence variation. Their family history includes one of 8 additional siblings that were affected. However, that sibling was deceased, so unable to be tested. However, they suspect a recessive mode of inheritance. A proband and the proband and an unaffected sibling were tested with the Illumina 610 quad bead chip to see if we could learn more information. Okay, so let's go back over into our data set. This is a different data type. This is the Illumina 610 chip. However, because Nexus is platform independent, we can still load it into the same project. Again, to load the new data, we would go to Load Data, select our data type. We would just scroll down now to Illumina. As you can see, there's a lot of different data types available. We would again select non-mosaic, again select our array, which is 610, and now load the data. Okay, as I mentioned earlier, all these data sets have been preloaded. Okay, so now we're going to click and select for these 2 samples. As I mentioned, one is the sibling and one is the proband. We're going to just add in some information here for the study, and also look at the samples here. Okay, so we can see that the top one is the male proband, and the bottom one is the unaffected sibling. also rename our samples. Okay, so we're going to just type in the gender, and now when I hit return here, this is going to become unprocessed. Great. And rename our samples. Okay, now we're going to, again, reprocess to correct for that loss of the X chromosome in the male. As you can see, it's very fast. Perfect. All right, and let's use our slider to zoom in. Okay, so this is a little bit more noisy than our last array, but that's okay. We can actually use the filter to clean up these results a little bit. Let's click on this. Oh, we didn't clear out our old filter. Let's do that first. Okay, there we go. So this is our raw results. So you can see here, like we said, it's a little bit messier, but we can clean this up. So one of the first things that we want to do is we know that this is a suspected recessive mode of inheritance, which means that these gains are not likely to be the calls that we're interested in. So the first thing that I want to do is filter out the single copy gains and high copy gains. So I'm going to go over here to the filter options and do copy number events, remove high copy gains and single copy gains. I'm going to click OK. All right, so now we're left with the loss of heterozygosity regions as well as the single copy losses and homozygous deletions. De novo or unique in the proband, but not in the unaffected sibling. So we could, again, if we wanted to, apply a bed filter to remove the calls. However, there's really not very many calls in the proband. So I'm going to just do this old-fashioned way and click in through it. So what we can do is we can just zoom in specific regions. So here we have a single copy loss. However, this is intragenic or not within a gene. These ones are all shared. This one right here is unique. However, it's in this Cub-and-Sushi domain protein, which is one of the longest genes in the genome. It's frequently hit by things and is rarely of interest. So we're going to just whiz right past that. Okay, this one is also shared. This one is unique, but it's also not within a gene. And these two over here are also unique, but both of them are not within genes. So we can see that we have several de novo changes, or de novo losses, I should say, in the proband. However, none of them are within coding regions. So now what do we do? Well, knowing that, and also knowing that as of now, most of the changes that are have been identified for causing OI are in fact sequence-related changes, the clinicians at this point decided to look at the proband and see if they could identify any regions of interest that might be unique regions of homozygosity. As you remember, this is a child from consanguineous parents, so there are some long stretches of homozygosity. And because this is a recessive mode of inheritance, this could lead to potential regions where he could have a homozygous mutation. So what we can do is we can now apply another filter. We're going to get rid of all of the copy number calls since we didn't see anything of use there. And we're also going to filter the allelic calls based on size. So we're really they started with a 300 probe length to see if they could find any regions of homozygosity that were larger than 300 probes and unique to the proband. So we're going to apply these filters. You can see here I have a pop-up window that just asks me if I want to proceed. I'm going to click yes. And now we're going to see all of these losses are going to go away, and also all of the smaller yellow loss of heterozygosity regions. And we're left only with the longer regions remaining. Okay, so now what we can do is we can see that in the sibling there are some regions of LOH, and then in the proband there are some other regions. We're really interested in identifying those regions that are unique to the proband. Two, this one on 4, and these two on 12. These two that are on 11 are shared with the sibling, or at least overlap with the sibling. Now what we can do if we click into the proband, again, we're actually interested in identifying genes of interest within these regions that we might want to use for targeted sequencing to help diagnose the cause of his osteogenesis imperfecta. So what we can do now is we can go into this chromosome button, and we're going to view the table of our results. And what we could do here is we can actually select what are the regions that we're interested in. So we said we want the first two on chromosome 2, but not the last one. We want the one on chromosome 4, not the ones on 11, and both of the ones on 12. So now we have our regions of interest. We have the event, which is that loss of heterozygosity, the length, the cytoband, the CNV overlap, and then the calls. But we don't have any information right now about the genes, and that's really what we're interested in. So what we can do is we can click on this Modify View button. And you can see here there's actually a lot of different options of additional information we can add in. So we can add in all, down here on the bottom are all of these different types of gene tracks we can add information for. On the middle section here, we have the gene symbol counts and IDs, which we're going to add. And then on the top panel, we have some just And so now what we can see is we can actually export this table. We'll get just these 5 calls that we're interested in, and we'll have gene lists of all the genes that are in here. And this is one way to help narrow down the genome to just those regions of interest. Still a little bit of a list, but it's still manageable. Now, I'm going to save you the task of going through this and just say that there was, in fact, some bone morphology genes located within these regions, and so they were sent out for targeted sequencing. And now we're going to actually load in the targeted sequencing results. So what we can do loading guide and now click on sequence variation. We can upload this MAF file, and I'm just going to select our mutation file. Now you can see here it's been added in with the sample, so we have a second processed type here for the sequence variation. Those results in, and now we can see this red arrow is new. If we go over it, there's been a frame shift from a deletion that's been located in a gene, and it's in this homozygous region. So it's a homozygous frame shift, which can be deleterious. We actually zoom in. Get that nice and tight. It's this gene SP7. Okay, so let's learn more about SP7. We can right-click on the gene, link out to Ncbi. And we can see here that we are going to just go right over to this health section again. We do have some more results in ClinVar and in OMIM, nothing in dbGaP for this one as well. So let's click on ClinVar results. Okay, so it looks like there's 3 results here. One of them has been described as being pathogenic with OI, which is also what we're looking at. So this looks like that could be a good indicator. And we have another one that's listed right here. However, the phenotype is not specified. Okay, so it looks like we might have found the causative variation. If we go into OMIM, we can actually just look up this gene to read a little bit more about it. And if we click here, we can see that this is a transcription sector, and it is a putative master regulator of bone cell differentiation. So it makes perfect sense that if you had a homozygous frame shift mutation and a bone cell differentiation gene, you could have a bone-related disease. So it looks like we've also been able to find our significant variant in this case review. Okay, so let's go back, and now we'll look at case review number 3. So the first 2 cases that I presented with you today were both constitutional-based arrays, but some of you may also be looking at cancer samples. So now I'd like to switch gears and show you a sample review with a cancer sample. This is a 68-year-old female with acute myeloid leukemia. Her bone marrow biopsy results revealed 55% blast cells, which is very high. Molecular analysis that was targeted was negative for BCR-ABL, FLT3 mutation, and activating RAS mutation. Her cancer cells, as well as unaffected normal DNA, were tested with the Affymetrix SNP6 array, as well as whole exome sequencing. So we have both sequence and copy number information for her. All right, let's sort by this. Let's add in her information here. So this is now our AML study. And take these samples for viewing. Okay, so we're going to first look at, we have, like I said, normal DNA that's unaffected as well as for cancer. So let's first view those. We also have the sequence variants that are found within her cancer cells. These are the somatic variants, meaning that they're only in the cancer. Oh, and we have to take off our filters. We can view everything. Great. Okay, so what you can see is we now have our gains and losses are shown here. Our top panel actually right now is showing us our allelic changes, so let's just adjust this view. If I go into aggregate, I can change it back to copy number. And so we can see we have, in the normal, we have germline gains and losses. These are just her normal CNVs that are present in her genome. In the cancer, we have some gains and losses that are also these germline changes as well as somatic changes, meaning changes that are found only within the cancer cells. Typically, when we do cancer analysis, we're interested in identifying those cancer unique changes. So one thing that we can actually do is we can fix this analysis to remove those normal calls. Now, I've shown you different ways of filtering out the data, but we're going to actually do this a slightly different way. We're going to do a pairwise analysis. If you only are comparing your sample with one other sample, you can actually do a pairwise analysis where you're literally subtracting the calls of the normal from the cancer. And so to do that, we would load the data with the descriptor, which is this other option down here. It's just a file that identifies which one is the sample that is being subtracted from the other. And so we're going to add this one into the view, and I'm going to call this somatic because that's showing us only the changes that are in the cancer cells as opposed to all changes. And so you can see that it really cleans up the data. So we have here now, again, all of those mutations. If I hover over them, we can see what the mutations are. This one's a missense. We still have our gains and our losses. We have some larger changes as well as small ones. We also have these small regions that are somatic copy number neutral changes. So these are areas where there's loss of heterozygosity that have occurred within the genome. And so now we want to, take a closer look at this, at these somatic changes. So we can see here, if we just look into it, let's click into this view a little further. So we can click into this individual sample if we want to just look at it on an individual basis. We go over to the Overview tab. You can see that there is this large gain on chromosome 21, which also coincides with a mutation change. So I think we'd like to look at that to see if it's of anything of interest, because there is a potential for this mutant to be gained as well. So if I click on that chromosome, it's going to bring me right over to the chromosome tab. Okay, we can see here now we have our gain of the whole chromosome. We have the lower panel is showing us this actual call. We can see that there is, in fact, a substantial shift up in the call. And also we have our probes have this nice split, which we expect to see when we have allelic imbalance from a single copy gain. We also have this mutant right here, and I'd like to find out what it is. I can click on this R, which is locate a region. Click on the change, and it's going to pop up the table down here. We can see it's a deletion right here in a gene. I don't know what gene it is yet, so let's modify our view and add the gene ID. It's the gene RUNX1. Okay, so RUNX1 is something that we hear a lot about in leukemia, but if I didn't know about it, I can always click on it. I can link out and learn more. And so I can go here. This time I'm going to go to OMIM. I'm just going to click on RUNX1, and we'll see that it's a transcription factor, and it is associated with AML. So it looks like this could be something of interest. We also observed this copy number change, which was this large gain of chromosome 21. Now, I don't know, when I'm just looking at this individual case review, if this is a frequent gain that we see in cancer or in AML, or if this is really unique. So what I can do is I can go back to the Nexus DB, and I can actually query some other projects to see if this is a frequent change. So because we're now interested in cancer, I'm going to look at some of these GSV projects. These are a bunch of different cancer database projects that we can search. And I'm going to actually just select a whole bunch to start with. You can always pick specific ones, or you can just pick generally to query a larger set. I think that looks good to start. Okay, and so we've selected our projects. Now we can click over here. We can select the Query Database button, click on the change, and now it's running through. Nexus is looking at all of the samples in all of those projects to see if this large gain of chromosome 21 has been frequently reported in any of these other samples. You can see that it's taking a little bit longer because we are querying a lot more information this time, but it's still going to be a relatively fast process. Okay, and so while that goes, so once we've decided if this is interesting, one other thing that we can also look at is identifying if looking for ways to confirm our results. Oh, looks like it's ready. Okay, let me just step back for a moment. Okay, so it looks like out of all those projects, 24 of them have a change. If we click on the samples, we can see 336 samples are actually contained within those projects that have a change. If we go here, we can look at the actual call. So we were querying basically the entirety of chromosome 21. You can see it's all gray. And there are a number of samples that also contain this gain of chromosome 21. We can actually click through here to see what projects they belong to and identify which types of cancers they're occurring in. But you can see that it is a fairly frequent change. And if I wanted to be very specific, I could have just selected something that focused on only leukemias so that we could know more about this specific cancer type. Okay. So now that we've queried the database and this looks like it's a real change, it is something of significance. We have this gain of, we also have this mutation of RUNX1, which could also be gained. Maybe we want to verify this change with another method like a FISH probe. Now I know this is a really long region, so a FISH probe might not be necessary for this particular change, but for other changes that might be a good option. We actually do have the ability to add in a track here that will show us all of the FISH probes. So let's add that track. I'm going to close this window, open this one up. Okay, if we go to options and track selection, one of the tracks that is available for us to view in Agilent is this SureFish track. So I'm going to apply this to it. We're going to see it pop up right here. Okay, now let's find that change again. That was this over on chromosome 21. You can see here now we actually have the SureFish catalog that's been loaded in, and so we can identify probes that we can order for any region. So if I wanted to specifically focus in on this RUNX1 region, I can just click on this button for the SureFish track, and it's going to actually take me right to the Agilent page so that I can find specific probes to order. So when you're doing your case review, if you ever find an example where you want to order a FISH probe, this is a really quick and convenient way to find it. Okay. So I do have some time. I wanted to go over one last case review. As you may be aware, with some case reviews we have a lot of information. This one we have very little, but we do know that it is in fact a cancer sample. And those of you who are working in clinical labs with cancer samples, you may be aware that sometimes everything is neat and tidy, like the last example, and sometimes they can be quite complex. So let's look at this one. This is one of the more complex results that we sometimes see. Okay, so if we're now just looking at an individual sample. This does not have any mutation data associated with it. It also does not have any normal data. We're really just looking at the cancer this time. If we click on the overview, we can see that it's calling a lot of copy number changes. We have losses with yellow loss of heterozygosity. We have a lot of blue gain, and some of these blue gains also have allelic imbalance. I'm noticing, however, that there's a lot of calling here all throughout the genome, and sometimes this can be a red flag. So if we click on the whole genome button, we can actually look at these raw results. And one thing that I'm noticing here is that if we look at this top panel, we have the copy number call, and the bottom panel is the B allele frequency calling. The B allele frequency panel tells us when we have states of balanced diploid, meaning that we have homozygous and heterozygous AB calls, and states of loss of heterozygosity where we have only AA, BB, or if we have single copy loss, only A and B calling. And so you can see we have extensive stretches of normal diploid calls on chromosomes 2, 5, 7, 9, and 10, and so on. However, if we draw our attention upwards, you can see that all of these regions are also calling single copy gain. Now, what looks like has happened here is that our baseline ploidy needs to be adjusted. When you have a sample that strays from its normal diploid state, sometimes the baseline ploidy calling gets to be a bit off. And again, if you've seen complex cancer samples, you notice that this can happen quite frequently, and what you often have to do is manually figure out what is 1 copy, what is 2 copies, and what is 3 copies, and so on. This can be a difficult task, and it does require a lot of double checking. Nexus has a great feature that allows us to correct for this. If we go over here, we have this set diploid regions. I'm just going to click on it. We have this now drop-down box, and we can specify regions that we have determined to be a diploid or balanced state. So we can type in here. I'm going to just pick chromosome 2. We can also highlight by clicking and dragging. So I'm going to identify these regions in 9 and 10. Add region, you can see it just pops up right here. And now I'm going to hit apply. And what Nexus is going to do is it's going to take these regions that I've identified as being diploid, and it's going to set them at the baseline. And so now we can see that chromosome 2 is baseline, and everything that shared that same numerical value has all been shifted down. 9 and 10 are baseline. Our losses are still low. And now this region over here is that is as a gain with the allelic imbalance. If we click on our overview, we can visualize this clearly. We now see that we have loss with loss of heterozygosity. All of these regions that were showing the gain without allelic imbalance, which we do not normally observe, are now neutral, which we expect. This region is showing a gain with allelic imbalance, and everything else looks perfect. So this is just one of the great tools that's really useful if you're doing a lot of individual case review for cancer samples, and you may need to sometimes do these ploidy adjustments. Okay, so with that, I think we'll wrap it up. In summary, I've shown you today a platform-independent copy number and sequence variant analysis. We visualized both constitutional and cancer samples. I've showed you custom filter options to find variants of interest. This included creating a veg file to remove parental calls. This also included adjusting and removing calls of gains in the OI, and also filtering out the smaller regions of loss of heterozygosity in the OI set. I showed you how to query public data sets within NexusDB. This included both the constitutional and cancer data sets. And I also showed you ways to link out to other search engines so you could learn more about your genes and regions of interest. If you guys have any questions, if you want to view our blog post or webinar archive, or if you have information, want to get more information from the software, please visit us at our website, biodiscovery.com. And with that, I'll take any questions you may have.
In the polls, we'll go to the questions now. Is there any way to easily copy and paste bulk amounts of data into a Nexus project?
That's a great question. So today I showed you how to add these factors in one by one. But if, for example, you had a lot of information in an Excel spreadsheet or even multiple Excel spreadsheets, you can also load all of this data in using this load factors option. Everything needs to be in its .txt form, and as long as your sample ID over here matches, all of that information will get uploaded right into it. So this is a really easy way to add in a lot of data all at once from your Excel spreadsheets that you might currently have.
Great, thank you. Next question, could one directly upload GSC series from Ncbi Geo to Nexus Copy Number?
So if you can download that data from Geo, as long as you have the raw or segmented data, you can upload it directly into Nexus Copy Number. You do need to download it from the Geo project, but yes, you can. And also, if the projects are already uploaded into NexusDB right here, you can click on these projects and download them directly from Nexus into your own data set. So you can go in either direction depending upon where the project is currently housed.
Great. Are there differences between Nexus Copy Number and Nexus Solar regarding the new features in version 7?
So Nexus Solo allows you to look at one sample at a time, but it does have the same features in terms of the filtering options and viewing Nexus DB. So all of those are going to be the same, but you are going to be limited at looking at one sample at a time.
Great. Can calls made by the software be adjusted? For example, can we join two calls into one because they might only be separated by a single probe?
Sure. So that's something that we see frequently occurs more often in the cancer samples than in the into the constitutional samples, but it can occur in both cases. So let me just open up a sample to show you an example of how we would do that. So here we have an example of the, just hide some windows here so I can see you all. Okay, so let's see. There's not anything very good on this example. Okay, let's pretend. On chromosome 15 here, here's a good example right here. So we can see here that we might have this region that has a gap in it, either due to a lack of probes, or, for example, sometimes you may have just a very small number of probes that fall outside of your threshold so that it gives you a false call of a breakpoint. And you want to join these calls together. There's this feature right here in Nexus that's called Add Join Region. And to do that, you need to select your region of interest. So here we would say we want to do it for this whole area. And we can click on the button here. And now we can join together these two calls. So it's going to give us the chromosome region, and we're going to add here what kind of a change it is. So this would be a loss. We can classify it if we want to. And now we can also add in notes. It'll also add in a note saying this has been manually called. And this is a great way for us to remember that we were the one that joined those together and that it was not made by the software. And then once I click OK, this is now going to be read all the way across. So this is a really great way for you to make any edits to the calls that you're currently seeing, which, you know, as I said, it does happen from time to time, and especially when you get calls that are very close to the threshold line.
Right, thank you. Can you please show again how to subtract calls in one sample from another sample?
Sure. So when we were doing this matched paired analysis, right here with the tumor and normal, we, instead of loading as data, we clicked on Load Descriptor. This allows us to select a specific file that has identified which sample is considered the tumor and which is the normal that's going to be subtracted. If you want to use a descriptor file, we have several different templates that are available within the folders in Nexus. And of course, if you ever have any questions or need help setting it up, you can email us at support, and we can help you to get exactly the right file that you need.
Is the quality index for Illumina systematically smaller than for Affymetrix? And if yes, why?
So every array has a different range of quality scores that we typically observe. This has to do with the variability in the differences of probes and the technologies used between different arrays. Overall, a lower score is always considered better than a higher score, but the ranges do vary depending upon not only which brand of array, but also the type of arrays that you use. And the cutoff thresholds are also going to be variable depending upon which one you're going to use. It mostly has to do, though, with differences in the actual probes and the technology.
Can we filter out the copy number variations from DGV, for example?
Yes. So when I was showing you our custom filter options, let me just open up that window so we can all look at it together. So when I was showing you our filtering options, you saw here that we could filter events based on copy number calls, just the overall blanket call of gain or loss. We could do it based on region, allele calls, but we did have this region-based filter. And if we click into here, you can see that along with the custom bed track that I created, there are a number of bed tracks for everybody to use. One of these includes this all DGV track, which is going to remove all of the variants that are frequently reported in DGV. We also have bed tracks that you can upload for not necessarily filtering, but just for viewing, things like cancer genes, if you're interested in cancer, developmental delay genes, haploinsufficiency genes, anything like this. Really, any gene list that you want to make a custom track from, we can. And it's a very simple process.
Great, thank you. There are a number of questions about Nexus DB here, so perhaps it might be good if you could go over the concept of a project in the desktop application, as well as what is exactly Nexus DB. For example, how is the data uploaded, when it's deleted, who's responsible for the keywords in Nexus DB, etc.
Sure. Let me find my windows here. Give me one moment. Oh, I lost it. There we go. Okay. Thanks for your patience. Okay, so for Nexus DB, the way that it works is when we want to use, we have right here on this dataset tab is our own personal projects. We can have multiple different projects. Only one is opened at a time, and these are projects that are kept locally on our computer or on a shared network drive, depending upon how we've set it up for ourselves. However, these are all the projects that only we can view. If we click here on Nexus DB, you'll see that this is another tab in Nexus. Now, these are all different projects that are available on our Amazon Cloud server. I can choose if I want to upload the projects in my projects, and these are things that I can put up in the cloud if I want. Right now, I don't have any projects that I've loaded up in there, which is why it's blank. There's another tab here that's called Vista Projects, and these are all of the projects that I'm currently able to access. This includes all of the public projects that we've posted, as well as any private projects that I am a group member for. In my instance, this is mostly public projects that we're viewing. And so you can see here now we have a checkbox here for which ones we want to use for our query. As I mentioned, you can query everything if you want, or just specific ones if you see something of interest. We have the name of the actual project, and this is defined by the person who's uploaded the project. We have a description of the project, and if you hover over it, you can see here all of the text. If you click on it, it'll actually give you more information as well down here. And again, this is all up to the person who's created the project. We also have keywords to define it. This is just the short-term words and for the individual project. We have a list of the number of samples, the organism build, and then the platform for the project. And finally, we have project owners and who is able to view it. And you can see here that these are almost all public projects. Now, when we have an individual project here, there's a few different things we can do with it. We can simply use it to query. We can also use it to download, in which case we can actually download this data into our own projects we have open, or we can create a new one to use it alone. And if we want to download the project, we just have to click on the blue hyperlink for the individual project of interest. I'll click on this one here. And now it's going to show us all of the samples within that project, any factors that may be associated with it. And we just simply click on these buttons here to download the ones that we're interested in. This really is a nice way for us to share the publicly available information that's housed in a lot of different places. For example, the geodatasets or TCGA data. And as you can see here, if you want to view anything, you can just go ahead and do it. If there's anything that's missing that you'd like to see, you can always send us an email and we can see about adding it in. And of course, if there's any data that you yourself have that you want to share with others, you certainly can. You are by no means required to do so, but if you want to, that is an option. The only thing that's a requirement for you to gain access to this is you do have to have Nexus. You have to have an internet connection, and the first time that you use it, you will need to create your own password, login and password. If you have any more questions about Nexus DB, we can always, you can always add those questions at the end of this webinar, and we'd be happy to get back to you by email to explain further about how Nexus DB works and how you might, different ways that you might be able to use it.
Great, thank you very much. Another question here, can we use Nexus for methylation analysis?
Yes, so right now I'm showing you the the standard edition, which does not contain any additional modules, but you do have the ability to add on other modules, so we can also look at methylation and expression. Those are different add-ons, and if you look at our website, biodiscovery.com, and click on copy number software and view differences, you can actually see the different modules that you can add in, and it will also explain in detail which module will be of interest for you. There is one for methylation analysis as well.
Thank you. Can you explain how there is a loss but no imbalance in the B allele frequency?
Sure. So this is something that we observe sometimes in cancer samples when we have more than one clone that's present within the tumor or the cancer cell population. What sometimes can happen is that in approximately half of the cells, we're going to have loss of one copy of the chromosome versus in the other set of the cells, we have loss of the other copy of the chromosome. When we look at the cell set overall, we're going to be able to see that all as a single copy loss, but because we have some copies of, or some of them have copy 1 and some have copy 2 present, it's still going to present as a balanced heterozygous state. This is by no means something that happens frequently, but it does occur within cancer, and it has been observed with the combination of using these SNP arrays and being able to do karyotypic analysis. It's something that has been well described.
Great. Thank you very much. As we're almost out of time, we're going to stop with the questions right here. For any questions that were unanswered, we will follow up with you via email. And once again, just want to remind everyone that once this browser window closes, another one will open up where you can type in any other questions that you have, and we'll get back to you on those, as well as provide any comments or feedback you may have for us. And if there are any specific topics that you would like to see in future webinars, please do let us know in that comment section. Thank you very much, everyone, for attending, and we'll hope to see you at a future webinar. Bye, everyone.
Bye.